then we go ahead with this topic, approximation algorithms. So this is going to be the last lecture of the course, and I'm just going to give a couple of examples of where these kind of algorithms are in place. And again, this is going to be a very, very brief introduction to the field of approximation algorithms, which is by itself a huge field, and a lot of research happens in it. But this is just to give you a flavor of what kind of things are done there. Okay, so these are algorithms that run in polynomial time. But instead of exact solution, they output solutions, or instead of optimum solutions, they output solutions which are close to optimum. And this happens because the problems are generally, for which approximation algorithms are used, are generally NP complete. So you cannot get optimum solution in polynomial time, right? So you want close to optimum, but how do you show that? That whatever this algorithm is producing is close to optimum, because the problem is that you can't compute the optimum actually in polynomial time. So how do you give the guarantee that whatever you are giving is close to optimum? Right. So how does this affect this, and how do we argue about the optimum, that okay, the algorithm whatever it's giving is. So basically we'll be using some lower bounds on optimum, and we'll see how that, instead of the exact optimum, we'll use some lower bounds on optimum. Okay. Suppose this is a minimization problem, so we'll be using some lower bounds on optimum. So the first problem that we'll look at is the load balancing problem. And what does the load balancing problem have? It has M machines. Let's say M12 or big M12, MM, N jobs, 1 to N, let's say, and times for jobs. Let's say T1 to Tn, right? And what do we want? We want an assignment of jobs, which is a function from N to M. So if AI is equal to J, that means job I is assigned to MJ. So what are we going to look for? We are going to look for the assignment. This is what we are going to look for. And what is the quantity? So let's say that if some jobs are assigned to a machine, then how much time does a machine work for? Let's say Ti is equal to summation of Tj such that J belongs to AI. No, sorry. Yeah. Sorry, I did something wrong. No, this is fine. No. AI is maybe the assignment of machines to jobs. Just a moment. Let me just get that correct. Yeah, so AI is set of jobs that, okay, so this is not a function actually. So it is done the other way around. You can take the inverse of this function the way I had written, but okay, so here AI is set of jobs assigned to machine MI, right? And how much time a machine runs for? A machine runs for TI time, where TI is summation of all the jobs, running time of all the jobs, which are assigned to that machine. Okay, good. So this is what, like, this is called the load of a machine. And this is what we want to minimize, the maximum of this, right? So what is this quantity called make span? Make span is defined to be max over all j tj. Like, what is the maximum time a machine runs for, right? And what do we want to do? Question is, or task is, to find an assignment with minimum make span. And the decision version of it can be, which is NP complete, is given M machines and jobs, does there exist an assignment? And jobs and maybe an integer k. Assignment such that make span is less than or equal to k. Okay, so this is the decision version, and as I said, this is NP complete. We are not going to show it that this is NP complete, but like it is, just like for now, believe that it is. Okay. So one way of doing this can be, just do it greedily. We don't know, like, how to achieve the optimum, but what we do, go through all the jobs, in any order, okay, and assign the current job to the machine, or a machine if there are many, like, you break ties arbitrarily, which has the smallest load so far. Okay, so this is the algorithm. So let's just see it in, like, pseudocode. So what does the algorithm do? It looks at start with no jobs assigned, and set ti is equal to 0, which is the load of, so this is load of machine I, and ai is equal to, empty set for all machines mi. And for every job, let mi be a machine that achieves the minimum current load, tk. Assign the job j to machine mi, increase the load of the machine, add the job to the machine's assigned jobs, and increase the load of the machine. And you keep doing this, right? And finally, what you can do is find, so this you can do it in an array, and then you can find min over all j, sorry, max over all j, tj, right? That is going to be your make span. And if you are given a k, then you can compare this with the k, like, the usual drill. Okay, so is the algorithm clear? If not, we just see an example and that will make it clear. So suppose you have 3 machines, M1, M2, M3, and suppose you have 6 jobs, 2, 3, with running times 4, 6, 2, and 2. So let's look at how the algorithm will assign these things. So first the job 2 comes. So let's say it gets assigned to M1. Then job of length 3 comes, it gets assigned to M2. Then job of length 4 comes, it gets assigned to M3. So this is 2, 3, 4. Then 6 comes, and now the minimum is M1. So you put it on top of this. This is 6, let's say. This is 2. Now this is the minimum. And then this is the minimum. Right? So what is the make span here? What is the make span for this example?
8.
8, right? And what is the optimum? So let's say optimum, let's draw in green here. How can we do optimum? So what we can do is put this 6 on one machine itself and transfer this 2 to here. It will make it 7. So 6, this is 3, 2, 2. Right? And then again, this remains the same. So what is the optimum make span? What is the optimum make span here?
It's 7 now.
7. Okay, good. Can it be less than 7? Can we do better than this? So we want to claim that this algorithm, you think about that. Then can we get less than 7? The algorithm achieves close to optimum. Right? But how do we do that? So we need some lower bound for optimum. So that is why I'm asking you to find a lower bound for how can we say that this 7 is optimum, let's say.
Sir, can we say that the sum is 19? So 19 by 3 has greatest integer 7. So basically,
Exactly. Yeah. So the total is 19. So some average has to be there on at least one machine. And since every job is integer, it is going to be integer. So in this case, we can, determine that, okay, it cannot be less than 7. But that gives us an idea of how to, have some lower bound on the optimum, right? And why do we need a lower bound? Because we can't find the exact optimum, right? In polynomial time. So we need some lower bound, right? So just like you said, the first lower bound is going to be the average. So let's say lower bound 1. We'll just say that optimum make span is at least T star. Let's say optimum is T star. That is greater than or equal to 1 over M summation of all Tj. Right? That some machine has to have the average many jobs. Okay. But this is not very good, why? Because Suppose you have 100 machines. And let's say 100 jobs as well. And 99 jobs have time 1. And one job has time, let's say 101. Right? So what is the optimum make span in this case?
One 101.
101, which is what the algorithm also achieves. But what is the lower bound that we get if we apply the same lower bound?
Two.
You get T star is greater than or equal to 2, right? So we have like this 2 and we want to compare it to 101, which is much higher. But even though our algorithm is performing well, our lower bound is not that useful. Right? So now we want another lower bound. So what are we missing in this lower bound?
So the maximum value of all the TIs.
Exactly. So if we add that, now that is another lower bound. What does it say? That optimum make span is at least, now let's say T star is greater than or equal to max over all j Tj, right? Because this Tj has to be assigned somewhere. So the max span is going to be at least that much. And now with these two lower bounds, we are ready to prove. And what do we prove? The lemma says that algorithm, whatever was the name of the algorithm, let's say, what was the name? Greedy balance. Produces an assignment of jobs with make span T less than or equal to 2T star, where T star is the optimum make span. Okay, so this is what we want to show, that no matter what jobs or machine we get, this algorithm, which is the greedy algorithm, the simple algorithm that we saw, this always produces an assignment with make span that is within a factor of twice of the optimum make span. Okay. So let's look at the proof. And the proof is, the idea is going to be that for a machine MI, look at the job J that is last assigned. MI, right? Now, if J is small, if Tj is small, then use lower bound 1. And if Tj is very large as compared to other jobs, then use lower bound 2. Right? So already we will say that if Tj is small, then already all the jobs are small, and whatever we are achieving is not very far from the optimum, because we have a sort of average as a lower bound. And if Tj is very large, then it itself will determine that, okay, what we have is not too much. But let's say, take any machine MI. Now let's fill in the details. take machine mi. Let j be the last job to be assigned. So when j is assigned, what is the load of this mi? What is ti? This is ti minus tj, right? Sorry, let's just say load is equal to ti minus tj, where ti is the final load and this tj is the length of the job that we have just assigned, right? But we also know from the algorithm that every other machine has at least ti minus tj load, because we are assigning the job to the machine with least load, right? So let's sum the total of all machines. And what do we get? That is at least m times ti minus tj. Or we can say that ti minus tj is less than or equal to 1 over m summation k tk, where this is the sum of the loads, right? And what is the sum of the loads of all the machines? So in fact, you can take the machine mi for which the last job gets assigned. Or actually, we don't need that. That's fine. So what is this? This is going to be at most 1 over m. What is this quantity going to be? This is also summation of all the tjs, right? At most. Okay, let's use some other variable, ti's, because j we are using here. In fact, I also we are using. So, some other. But it's okay. I mean, this is just bound here, so let's call it I. Is this clear, or if there is any question, please ask. In fact, we can do it slightly this much actually. Right? But let's, forget it for now. Let's just say summation of ti. Because this is the sum of load of all the machines, and sum of the load of all the machines is at most sum of the load of all the jobs. Okay. And what is this quantity? What do we know this? What do we know about this from lower bound 1? What does lower bound 1 say? That this quantity is at most T star. What happened? Everybody is silent. Is there any question, anything? Please ask. Kushbu, Ayush, are you understanding? Shubh?
Yes, sir.
Okay, so fine. So now we have done this, and now what is left is just Tj, right? So since we have taken any arbitrary machine, actually, we did not take the machine which, like, we have just taken any arbitrary machine Mi, and we are looking at its jobs. And we saw that Ti minus Tj is at most T star, and Tj itself, we know that T star, right? Using lower bound 2. So now we sum these up. So call this 1, call this 2, sum 1 plus 2, and you get that Ti is less than or equal to 2 T star. This is what we wanted. So Ti is less than or equal to 2 T star for all I, basically, since Mi was arbitrarily chosen. Ti is less than or equal to 2 T star for all I. And that means that max of over I, Ti is less than or equal to 2 T star. So T is less than or equal to 2 T star. Okay. Any questions? Okay. If not, then let's go ahead and try to improve this. Okay. Another thing, which is that actually this is the, can we do a better analysis? One can ask. That, maybe this algorithm achieves better than 2, the, the ratio of with the optimum. But the answer is not really, like just a bit slightly, but not really. It cannot do much better than 2. Why? Because let's take M machines and N is equal to M minus 1 plus 1 jobs, where M into M minus 1 jobs have or require time 1, and 1 job requires time M. Okay. So what will the algorithm do? What is the make span it will achieve? Suppose it goes in first, it goes for these jobs, and then it goes for this job. Then what is the make span this algorithm is going to achieve?
2m minus 1.
2m minus 1, right? Because first it will assign these m minus 1 to m machines equally, 1 by 1. So you get m minus 1 plus finally it will assign this to another, right? So this is, you get 2m minus 1, right? What is the optimum?
M.
M. Why? Because you can just assign this one job to one machine. And distribute remaining. So one gets M and the other gets these M minus 1 machines get M jobs each. So optimum is M. So what is the ratio here?
Close to 2.
2 minus 1 over M, right? So which is close to 2 for large enough M. Or you can keep increasing M to get arbitrarily close to 2. And in fact, for the algorithm itself, you can show, like I was saying, there was slight slack somewhere. So for the algorithm, you can actually show that t is less than or equal to 2 minus 1 over mt star. And this is essentially now tight because this is what is achieved by this example. Right? This is tight. So this is a good exercise. Try to see that, how we can get, this slightly more from the algorithm. We have not tried that hard, but if you try just a bit more, you can get this. This is not very hard. Okay, good. So this algorithm does not improve, but what about better algorithm? So what were we doing wrong in the algorithm with this counter example that we got away from the optimum? How we could do this better? If we want to do this counter example in a nicer way, what could we do?
Maybe sort.
Exactly. So sort the jobs, because what happened was that, we equally distributed all the small jobs on all the machines, and then one large job came, which, maximized one guy's, load. So sort the jobs in, let's say, decreasing order. And use the previous algorithm. Right? And that is exactly what this algorithm does. Okay, so what is this algorithm doing? Start with no jobs assigned. Initial condition is the same. Sort jobs in decreasing order of processing time tj. And then again, the same thing that, let mi be the machine with minimum ktk, assign job to machine mi, and then find this. So that is the only thing we did. We just sorted the jobs according to their running times. And now we want to show that this actually achieves, a better approximation ratio. And for that, we show a lemma. So first thing is that if there are only m jobs, then our algorithm less than or equal to m jobs, then our algorithm already achieves the optimum because it will give one job to each of the machines. Okay. And what does the lemma say? Lemma says that now suppose there are more than like at least m plus 1 jobs. So if there are more than m jobs, right, then t star is greater than or equal to 2t m plus 1. What is t m plus 1? Is m plus 1 largest job. So you sort the jobs in this order here, t1 to tn, where t1 is the largest job and t m plus 1 is the m plus 1th largest job. So any idea about the proof of this lemma?
A machine will have to do a job twice, at least one machine.
Say again, sorry.
At least one machine will have to do the job twice, like.
At least this much twice, yeah, right? So just look at the first m plus 1 jobs. All of them require time greater than or equal to tm plus 1. And at least one machine will have to do 2 of them. Right? So that means that t star is greater than or equal to 2t m plus 1 or tm plus 1 is less than or equal to t star by half. And that's it now. Now we can show, like, just like the previous algorithm, that algorithm sorted balance produces an assignment. Any guesses? What is going to be the ratio? With Makespan? What is the number here? Here we have t star by 2. And earlier for that job, what was the bound that we had? For each
3 by
job, what
2
was the bound that? Yeah, say again.
3 by 2 T star. 3 by 2
by
T
2.
star.
Yeah.
M is 2 years.
You missed what?
2 minus 1 by M, the M will be 2 here. So
Yeah. Okay, so this is it. And the proof is really simple. So let Mi be the machine which has the highest load. Okay. And if Mi has just one job, it is already less than or equal to optimum using lower bound 2, right? Or sorry, yeah, it's fine. And if Mi has more than one job, then let J be the last job that is assigned. To Mi, right? And it has time Tj. So we know that this J is greater than or equal to M plus 1 in the sorted ordering. That implies that Tj is less than or equal to Tm plus 1, which is less than or equal to half T star. And then, like previous things, we know that all the machines have load. We can show, like previous thing, that like previously, we can show that this Ti minus Tj is less than or equal to T star, like we had in the previous proof. And now we have Tj is less than or equal to half T star. So sum them up, Ti is less than or equal to 3 over 2 T star. And this Ti is what we had assumed, that Mi is the machine with highest load. So that means T is less than or equal to 3 over 2 T star, because since Mi is the machine with highest load. So we just did that for the last job, we got a better bound. We did not compare it to T star. We got a bound for it, which is half T star. And that gave us a better bound for the algorithm, for this algorithm. Okay. Good. So these were the two algorithms I wanted to do for Makespan. I want to do one more algorithm very quickly because it has a mathematical flavor, and it is for vertex cover. So it's linear programming based approximation for vertex cover. So I'm not going to define the problem again. So question is, And here I'm going to, whenever we talk about approximation, we are going to talk about optimization question. You can convert them into decision versions, in a simple way. So given G comma K or just G, find minimum sized vertex cover. Find a minimum sized vertex cover. So sometimes, so why I want to introduce this problem, because sometimes what happens is it is better to formulate this problem in a mathematical way. And that is what, so you can formulate actually this vertex cover problem in an linear, as a linear programming problem. So what do we want to do? Suppose we want to minimize, so we have a variable for every vertex. So okay, so we have a variable xv for all vertices, and we want to minimize this summation xv subject to xu plus xv is at least 1 for all uv in E, and we want xv to be greater than or equal to 0 for all v belonging to V. So this is the linear program that we have for vertex cover, right? Now, if we wanted this xv instead of, so let's call it constraint 1, and let's call it constraint 2. So instead of constraint 2, if we had xv belongs to 0, 1, instead of saying it is at least 0, then this is exactly then solving, so call this LP1. Solving LP1 is equivalent to solving the vertex cover problem. So I'm not going to show this. So what does it mean? That G has a vertex cover of, so call this ILP. When we had this, instead of this constraint, constraint 2, if we have xv belongs to 0, 1. So G has a vertex cover of size K, if and only if ILP has a solution with objective value K, right? And that is very easy, because now you give this 0, 1, xv, you just give it 0, 1. And basically the 1 vertices you include in your vertex cover and the 0 vertices you don't include in your vertex cover. And that will satisfy every edge because of this constraint, because for every edge, one of the vertices have to be 1. Similarly, for vertex cover, for every edge, one of them will have to be 1. So this constraint will be satisfied. So this you can see for yourself. This is not very hard. Okay. But now that also means that ILP cannot be solved in polynomial time, because vertex cover is NP complete. Because essentially what we have shown is that vertex cover reduces to ILP, right? Where this is just the integer linear program, problem. So ILP cannot be solved in polynomial time because ILP is NP complete now. But this, when we say LP1, LP1 is just a linear program. So can be solved in polynomial time. Right? And we also know that, so let opt star or let opt LP be the minimum objective value for LP1, right? So what we know that vertex cover has size k if and only if the ILP has a solution with objective value k. So we know that vertex cover size of the, so let VC denote the size of minimum vertex cover. So we know that size of minimum vertex cover is equal to opt ILP, right? What can we say about opt LP and opt ILP? Is there any relation between them? So this is a linear programming problem where you can have the variables anything between 0 and 1 basically, and here you want them to be 0 and 1 only. You'll never need anything more than 1 that you can show, because you just want to satisfy these constraints and you will never need any value more than 1. So here you can take any values between 0 and 1. Here you want only zeros and 1. So which can give you lesser solution? Lesser objective value.
The LP.
Yeah?
The LP.
LP can give you lesser, right? So objective value of LP is going to be less than or equal to objective value of ILP. So what does that mean? That optimum of LP is less than or equal to size of vertex cover. Okay, so this is the equivalence that we have. So this gives a lower bound sort of on the solution. Okay, that the vertex cover size is going to be at least, so this is the lower bound that we desired for our approximation algorithm. So how do we get the vertex cover from a solution? From solution of LP? Because solution of LP is now going to basically give every vertex, you know, XV belongs to some value between 0 and 1, right? So from there, now we want to choose some XVs. So what can be a good choice? Suppose we want to choose those which have XV value at least half. Then can we say something about size of S? Anything about opt LP? Can we put something here?
Half.
Hmm?
Half.
Half or 2? Whatever the value of opt LP was, now I'm taking S to be the set which is the vertices which were more than half. So suppose there were vertices, so suppose it was like this: 0, 1 over 3, 2 over 3, half, half, something like this, right? Then we added all of them in my S. So my S has size 4 now. If all of them were half, then what was the optimum value of LP? Then it was 2. Right now also it's 2, right? No, right now it's 3. My S is 3 and opt LP is 2, right? But if all of them were half, then my opt LP was 2 and S was 4. For every vertex, we are going at most twice. We are including it as 1, while in the opt LP solution, it was at least half. Okay, Ritunjay?
Yes, sir.
Yeah. So this is 2 opt LP, and that is less than or equal to vertex cover. Right? Sorry, 2 vertex cover from the above. Using 1. But still we have not shown something. So we know that this S is at most twice the size of the vertex cover. But what we have not shown? We need to show something else, like one small thing. That S is a vertex cover. Because whatever solution we are outputting, it has to be a vertex cover, right? And how do we show that? How do we show that S is a
As
vertex
an
cover?
vertex from S.
Every
Every edge has a vertex from S.
Every edge has a vertex from S. Why? Because for every edge, we know that XU plus XV is greater than or equal to 1. So min of XU XV is greater than or equal to half. So at least 1 of XU, U and V is included. No, sorry, not min, right? Max. So at least one of them will be at least half. And so at least one of U and V will be included in S. Basically, what I'm saying is that since this constraint is satisfied by LP1, by a solution of LP1, at least one of XU and XV will have to be half, and that will be included in S. So S is a vertex cover, and size of S is less than or equal to twice size of vertex cover. So this is a 2 approximation algorithm. And we have, seen that, or not seen. Actually, we know that linear programming can be solved in polynomial time, and this rounding. So this is called rounding algorithm because we rounded the solutions of the LP to integers, and from there we got a vertex cover. So this is called, and this is a very useful technique in approximation algorithms, that you write an LP for the problem and then you round it up to get the integer points, and then you take those points in your solution, and that gives you the, close to the optimum solution, right? So any questions about this? So this you should try and see. I mean, this is not very hard. That why, if we just ask the values to be 0, 1, then the problem is exactly as vertex cover. It is a, it is a reduction. It's a proper reduction. Okay. So that's all I wanted to do. I've taken more time, but yeah, this was the last class, and I wanted to introduce you to this LP formulations of some graph problems as well, which is actually a very, very useful technique. So any questions about this?
Yes, sir, I don't have any questions on this, but I wanted to discuss the first thing you mentioned in the class.
Yes.
I did not want to interrupt then, but you said that you are waiting for Dean Acad's mail, right? Then you'll decide how the major exam will be held.
Or any other official confirmation. I might as well talk to the head and see, whether he can confirm these things, and then I'll do that.
Yes, sir. I just wanted to bring into notice that I think CAG GSECI said yesterday that the dean won't be releasing anything official now. That is why I just wanted to bring that into your notice.
I'll have a talk with then senior professors for what to do about this thing, because I was not part of the meeting that you quoted in your thing, so I cannot like officially act on that. So
Yeah.
I'll talk to some senior people and decide what to do.
Thanks a lot.
Sir, it is just a request that if you can confirm by today, like we'll have to
I'll
like
definitely try to. I
tickets.
understand your problem, but understand it on my part also,
Yeah,
because earlier they had
yeah.
mandated that thing, and I also don't feel very comfortable, asking everybody to come back or whatever. But then if they are mandating that, and that was the last email that I have officially got, right, where they have mandated such a thing.
Professors changed the policy now, so like, yeah.
I know that, but I'm not those professors, right?
Yeah,
So
yeah, I get that. Like,
I have to act on my own, and I'll be responsible for my own actions, right? It's not
no,
that.
like, yeah, yeah, sure.
Okay.
Thank you so much.
So I'm trying my best to resolve it as soon as possible. Have trust in that, and I'll let you know as soon as I decide. Okay.
Yeah.
Thank you.
Thank you. So thank you for coming. Thank you for being part of this code. And
Sir, I have a doubt.
Yeah.
Not doubt actually. Like if we are asked in the exam to prove that something is NP complete, then
Yes.
usually we use some other algorithm or other problem and show that it is polynomial time reducible to that algorithm we are given in the question, right?
Not algorithm, problem. Yeah. So you
Problem,
start
okay.
from some NP complete problem
So-
and reduce that to.
So what problems can we use actually? Like what problems are we free to assume are NP complete?
SAT, 3SAT, vertex cover, independent set cover, set packing, and
Can
what
you like mail or something?
the class.
Inform us.
Huh?
Can you mail a list or something?
Okay, fine. I mean, whatever is done in the class and plus maybe coloring. But yeah, I'll mail a list. Like, that is not a lot, but okay.
Okay, sir. Thank you.
And sir, actually, the last few topics, the topics were a little skewed in the book, right? Like, not all the topics from each chapter were covered, and like not all the approximation algorithms.
Yes.
So if possible, could you share a problem sheet, kind of like
Problem sheet? I don't
like
what
we can't attempt all the problems from the back problems of the book, like for practice.
No, but then you can like go through and see which ones are there. Now I cannot sort.
Okay.
Like if you have understood the material, then that is fine. I mean that is too much for me to like go and look for
Yeah.
which problems are there and which problems are not.
No, like if you have something ready already, so.
No, I don't.
Yeah.
So
Thank you so much.
that won't be possible for me. Yeah. Okay. Anything else? So yeah, if not, then thank you for as I said, being part of this course. It was really enjoyable for me. I like really, teaching this course. I would, teach it again in future, and other courses also. Next semester is going to be advanced algorithms, so I'll be teaching part of it, not fully alone. And so yeah, please, I'll be happy if some of you join that also. And it was nice teaching you guys. Thank you for coming.
Thank you, sir.
Thank
Good
you.
luck for that.
Thank you, sir.
Thank you, sir.
Thank you, sir.